Hello all. Hi, I'm Ramesh. I'm working for DNV in Oslo, Norway. I'm very happy that today's topic uh, we have it's about nickel aluminum bronze propeller manufactured by Wire Arc Additive Manufacturing. And I am happy that we are presenting the paper at second European conference on the structural integrity of additively manufactured material 2021. And I have an agenda. I will go through this introduction and then a full scale experiment and test results and discussions and final conclusions, and if there is any question and answers. As you all know, wire arc additive manufacturing, it belongs to the direct energy deposition arc, and which deposits metallic material layer by layer on a high quality metallic base with optimal chemical composition and microstructure for a specific purpose. And it is done by a very strict controlled automated electric arc welding process. So how today's paper we are going to discuss is the main most of the component in maritime, which is like ships and offshore. The component has to be on a vessel from the entire life period of the vessel, which is normally around 25 years. So that means from the starting of the vessel, it has to function as it is from the starting how it was in the new building stage. So that gives more necessary testing to be done so that the component will function and fit for service for the intended period of time. So in maritime class, normally we take the component certification based on their functionality and the importance, and as well as how they perform on the seagoing vessels. So today's paper we are going to discuss more about the propeller. It is being manufactured by Wire Arc Additive Manufacturing. So propeller is a propulsion system. It's an important system in these ships because it makes the ship move from A to B with a constant speed and with some energy consumptions. So most of the designers, they do the design of this propulsion system in such a way that it is giving the full efficiency so that the fuel cost consumption is directly proportional to the speed and the consumption of the fuel also. So hence the propeller is always an important in the maritime industry for the ship owners, for the operators. They normally always have the propeller polished surface so that there is no drag or no other forces making it slowing down. And the material selected for the propeller have to have a good characteristic. It should have a very good seawater fatigue resistance, and it should have a high resistance to galvanic corrosions, cavitations, erosions, and also some impingement attacks. The most common marine propeller in the industry now is the CU3, which is called nickel aluminum bronze. That's the most of the conventional seagoing vessels having it. So when we see the casting propeller, uh, the castings are done which requires a lot of preparations. Normally the pattern making they have to do, and they have to do a sand mold and then pouring, shakeout, cleaning thing. Almost 20 to 30% of casting, if it is not done a proper solidification effect is there, then it will turn to be having a different microstructure and different thickness, and it will be rejected. So what uh, we decided to do is to try a direct energy deposition method by WAAM, and to make a benchmark on the process, taking into consideration that the propeller blade will have a lot of loads during the ship motion in the sea, because it has to maneuver, it has to reverse and start and stop. A lot of dynamic loads are acting on it. So we established a joint industry project, and in with Hyundai HHI, Korea, Evaluation Institute of Industrial Technology, S5 Metal and DNV, and we made a project saying that, okay, why don't we do a full-scale experiment test to find out what is the achieved results on the high stress area. As you see in the figure, the high stress area on the propeller blades are zone A and zone C, where you will have a different thickness coming out, and it is having a skewed angle. As you see in the FE analysis, the root on the A is more critical, where it takes most of the bending moment as well as these loads, and as well as on the top on the C, where the region have a low stress, but the dimensions there, it's very thin blade. So for a full scale testing, we selected to do a testing at the zone A and zone C, and compare the results both on vertical and horizontal direction. For this experimental process, we want to do a full propeller, which is to be printed on a casting hub, and it was printed to a 2 meters with a thickness of 70 millimeter at the base, and it slowly converged to 8 millimeter on the tip. So we took a CAD model, and then the toolpath design was established to check all the error softwares used, and then the data check was completed, and it was sent to the WAAM robotic arm 6-axis machine, and we had a lot of monitoring sensors to see the interpass temperature and the on the melt pool solidifications, and then by using optical pyrometry and as well as optical cameras, we were monitoring the diffusion, and then finally it was grinded, and it was having a non-destructive testing, and final product was done. The weld process parameters we used was the base material was copper nickel alloy. The arc process is gas metallic arc welding, and the welding consumable was standard copper nickel aluminum bronze. If we use this welding consumable, we do not require a post-LD treatment on the process. And also we use shielding gas argon 99.99%. We use a stinger bead, and minimum preheating we maintain around 190. And the arc weld machine was furnace CMT welding, and feed wire was by CMT control, and data acquisition was done by mobile system. The maximum interpass temperature was maintained for 250 degrees centigrade. And when we took the 4 samples at the critical part with horizontal and vertical directions, and it was sent for testing. Both we were interested to see the metallographic microstructure, how it on the root, which is on the base and on the top, because since it goes more thermal cycles, so we want to check how is the effect of heat affected zone on between the two layers again. But when we see the macro, we find that there is not much significant difference in the base to the top. So that means it has going through a same heat cycle, and also there is no defects in the inter melt pool boundary area. And this micrograph was similar to the earlier scientific literatures done by some academics on the wire arc additive manufacturing, especially on nickel alloy. And the results, when we compared with the normal castings, where we require a yield strength of 250, we achieved almost 330 megapascals or Newton per millimeter square, around 320, and tensile strength were approximately 700, 690. Elongation was almost within the range. And the choppy we have tested at 0 degree centigrade to see if the toughness property are being achieved, and the toughness property was almost more than the required, which is 27 joules. And in additional, we have done a hardness test to see what is the comparative value, and it's also achieving as per the results of the casting. So in other term, the mechanical results are more towards quality wise, it's more towards the casting side. And also we have done a chemical analysis on the as build to check whether it is within the range of the rule requirement, and it also meets the requirement. So the final propeller, it was the weight was around 520 kilogram with 2 meter diameter. It was polished and was keeping it. So the conclusion of this is that the WAAM process can be used for manufacturing a propeller if all the parameters are being strictly controlled and inspected, and as well as the tensile, ductility and toughness were found, and an isotropic along the build and deposition direction was achieved. And the toughness is also acceptable, and it is achieving 27 joule and above, and it meets the requirement given in our DNV rule for the ship rules. And based on this results, DNV have made and accepted the WAAM process for the components, and it is been accepted in the rule now that WAAM wire arc additive manufacturing as well as additive manufacturing is considered as one of the manufacturing method like castings, forging and rolling. But to accept the seaworthiness, we need additional experimental data to be done, like fatigue and thing. So that will be the next project. We are going to look into the fatigue of the nickel aluminum bronze. So this was the experiment we done on the full scale, and it was nearly a success between industry and academic project. And that completes the paper, and thank you for listening, and if there is any question answers, please raise now. Thank you.